is. Yeah, today we are presenting live out of Munich. And yeah, yesterday we were in Trier and in Waldenburg. And yeah, so I hope you stay tuned also for the rest of the sessions today. But today the topic is about fundamentals of capacitor technology and their applications. I'm very happy to welcome Lukas Hölscher today, who will do the presentation and also answer all your questions at the end. Lukas, hi.
Hi.
So then, before we start into the presentation, just some information from my side. You will be muted during this webinar, so you can't ask us your questions via your microphone, but of course you can ask us all your questions in the chat. You find that on the right side in Demio tool. So, and then after the presentation, we will just go through the questions, go through your questions, and if we can't answer them today in the live webinar, we will answer them via email afterwards. You will also have the possibility at the end to download the presentation, so you will also get that. And if you missed that, we also share the link with you in the next few days. So then I think enough information from my side. I think you all want to hear some information from Lukas. So yeah, Lukas, stage is yours. Have fun.
Okay, thank you. So, all right. Yeah, so first of all, hello from my side. My name is Lukas Hölscher, like Markus already mentioned. I'm technical project engineer for capacitors and resistors. And today we will talk about fundamentals of capacitor technology and their application. So yeah, in the end, I will start with technical basics, and I will also give an overview about capacitors and what capacitors are there in the market. Then we will dive a little bit more into the specific MLCC, film capacitors, electrolytic capacitors, and supercapacitors. And afterwards, for sure, I will give a summary. And in the end, I'm happy to answer your questions. So let's talk a little bit more detailed about the basics of the capacitor. So talk a little bit about the parallel plate capacitor, as you may know. So normally the parallel plate capacitor is based on two plates, and in between we have some dielectric material. And if you want to calculate the capacitance of this capacitor, you have to multiply the permittivity by the surface divided by the distance of the plate. And if you cannot change the surface and the distance of the plates, then you can change the epsilon r, which in the end means, or which is shown on the right hand side. So maybe just an additional information, the epsilon 0, which is a constant, you cannot change it, but the epsilon r, we can change it. So if we have a look at vacuum, for example, the factor is 1. And if you compare it, for example, with polypropylene, and polypropylene is used for a lot of film capacitors. And this means that if you have a factor of 2.5, then you can get 2.5 times the same capacitance in the same volume than if you compare it with the vacuum or with air, for example. And if you go a little bit more into detail and discuss, for example, aluminum electrolytic capacitors, these are more or less based on aluminum oxide, and this material has an epsilon r of 9.3. So this means in the end that you have like 4 times of the capacitance for the same volume compared to polypropylene capacitors. So you can really see, based on the physics in behind, that there is some benefit for aluminum electrolytic, for example. If we go more into detail about the ceramic capacitors, then you can see ceramic, especially class 2 ceramic capacitors, offer a lot of capacitance on a very small volume. We will go more into detail about the limits of it and so on later on. Also a capacitor is a passive component, and every passive component, they have parasitic side effects, like for example the ESL, ESR, for example, and we have for sure here we have the ideal capacitance, which should be as dominant as possible in our circuitry here. And if we have a look at the insulation resistance, then this insulation resistance should be as big as possible to reduce the leakage current here. If we have a look on the right-hand side, we see here the impedance curve over the frequency, which is constructed by the capacitive part shown here, the inductive part, and also the ESR. And if you sum this up, then you will get for sure the impedance. And at this point where the capacitive part and the inductive part is same, then we will see the resonance frequency at this point. So this is the region or the point where inductive and capacitive part is same. This is the resonant frequency. So let's talk a little bit more about the capacitor types or the different types which are there in the market. Generally, we can distinguish them between fixed capacitance and variable capacitance. Variable capacitance are used, for example, in laboratories and so on, but we will talk more about the fixed capacitor types or fixed capacitance types. In this case, for example, film capacitors, which could be based on paper film capacitors, plastic film capacitors. So there are two different main technologies. If we talk about ceramic capacitors, then we have to distinguish them between class 1 and class 2. If we talk about electrolytic capacitors, then we have the aluminum electrolytic capacitors, which also cover polymer capacitors and hybrid capacitors. And then for sure, there are also tantalum capacitors and niobium capacitors. If we talk about supercapacitors, then you will find mostly on the market the electric double layer capacitors or EDLCs. And there are also pseudo-capacitors or hybrid capacitors, but in the end, the function is from the outside more or less the same. You get a lot of capacitance, but fairly low voltage. Then there are also mica capacitors or glass capacitors, which are suited for higher voltages and very, very stable capacitance values, but are somewhat limited when it comes to how much capacitance can I really get in the same package. So yeah, you need a lot of volume to reach high capacitance values. And then there are also feed-through capacitors in the market for filtering of high frequencies. But today we will focus on the parts which we also cover with our portfolio. So let's talk a little bit about the overview and to make it more visible. I showed it here, or I show it here over the capacitance and the voltage range for the different technologies. And yeah, here you can, for sure you can see why MLCC, why they have the biggest market share, because you can get them with high voltage, low capacitance, and also higher capacitance. When it comes to higher capacitance types, as I also mentioned before, also electrolytic capacitors offer higher capacitance values, and you can get them with a medium voltage. If we talk about film capacitors, then there is an area in the high voltage and medium capacitance region where these film capacitors are also very suitable. If we talk about the supercapacitors, then you can see here on the right-hand side, these supercapacitors, they have a high capacitance, but they offer fairly low voltage. But they're in this region, a good solution. So let's talk a little bit more detailed about MLCC. And what I show here is the inner construction of an MLCC with the termination finish, the barrier layer, and then also the end termination or the external electrodes based on copper. And then you can see in the middle the dielectric material for class 1, which is based it is based on titanium dioxide, and for class 2 it's based on barium titanium dioxide. And what I also showed here on the right-hand side, this is a cross-section of a real existing MLCC. And you can see here, if we have a more close look into it, then you can see here the different plates, which are very, where the distance is very, very small. which leads in the end also to a higher capacitance. So if we talk about class 1 and class 2 ceramics, then I already mentioned it's very important to distinguish between class 1 and class 2. Class 1 is, for example, NP0 or COG in the US, which is a paraelectric material. The disadvantage of this type is that the epsilon r is fairly small in comparison to class 2, but the big advantage is that you have a low temperature dependency next to no aging. So to sum it up, you have a low capacitance but a very stable capacitance. If we talk about class 2 ceramics, then we have the opposite, or it's vice versa in this case. You can get high capacitance values like more than 100 microfarads, but you will have some dependencies like temperature dependencies, aging, and also some DC bias behavior, which leads to the fact that the capacitance will drop by applying voltage. And as I just mentioned, the DC bias behavior, I just showed here a typical curve of different ceramic materials. For example, the NP0 ceramic material, and then the X7R ceramic material. And you can see here that if you apply some voltage, you will get a certain capacitance drop. But I really want to make sure here that this can vary very much between the different components. So it's very important to check here, for example, our RIT expert for the specific measurement data. As I already mentioned, these are measurement data, and you can see also here our measurement setup. And what I want to show here is we compared here 4 different MLCC, all X7R, all 1 microfarad, all 50 volts, but we just changed the size. So in the end, this means if you reduce the size of this component and everything else will keep the same, then you will see that the DC bias effect gets even worse. So take care of this topic if you want to miniaturize your application, that you check if the capacitance is still enough for your application to work properly. One other topic for class 2 ceramics is the aging. Class 1 ceramic, as it's mentioned also here in this diagram, they don't show any aging in this case. But for class 2 ceramics, you will see a certain aging after the component leaves the production in this case, which is also more or less, which is also more in detail described in our support note, which my colleague Frank Bohane wrote. So if you have specific requests or if you want to have a more close look into it, then please check it. And if you have questions, please always ask them. And so here's described how this aging effect really occurs. What is also described here is that if you, after leaving the production, if your component will age and so on, that if you exceed the Curie temperature of the specific component, then you can reset this aging behavior. And we did also some tests, for example, to check what happens if you apply these, or if you do the reflow soldering with these parts. For example, these parts were stored for a longer time. And we can show here in this diagram that the parts more or less reset after the reflow soldering process. So afterwards, this whole process, aging process, starts again, but the reflow soldering will normally reset this process. So let's talk a little bit more about the capacitance yield in a total about class 2 ceramics. What I selected here was a 22 micron 1206 10 volt type. And for example, if you have a look at the data sheet, for some types is plus minus 20%. Normal data sheet tolerance, and then you will always have the temperature tolerance, which is for X5R, which is plus minus 15% over the whole temperature range. And this will also lead, in the worst case, for a certain drop. And in this application, or in this situation, we applied for this 10 volt rated part, we applied 6 volts, which also leads to a lot of DC bias. And this means in this case that you have minus 50% of capacitance drop. And then also we took some aging into account, aging over 10,000 hours, like a little bit more than 1 year. And you will also see some additional capacitance drop afterwards. So in the end, if we collect everything, we have a component rated for 10 volts applied with 6 volts after 1 year, and X5R high capacitance type. This will lead in the worst case that you have only 31% of the nominal value, and in the best case 63% of the nominal value. But I have to say that this could vary also for different products. But yeah, it's important to check the details here. So let's talk a little bit more about special types for MLCC. For example, what I already mentioned, there are some limits for MLCC. If you make MLCC as big as possible, so this is a ceramic material, and yeah, if you make ceramic material, it's very big. And if you have some vibration, for example, then these ceramic material tend to show some cracking or something like this. And to avoid this cracking, we implemented soft termination capacitors, which have a little bit flexible polymer, highly conductive polymer layer here in between in the termination, which leads to the fact that this can compensate some mechanical deformation in this case. Some other special cases are, for example, safety capacitors intended to use as X1, X2, or Y2 capacitors. And you can see here in the cross section, for example, we have here an internal series connection, to improve the safety of this part and also to improve the dielectric strength of this part. So let's talk a little bit more about film capacitors. Film capacitors, generally speaking, we could divide them into metal film and metallization on dielectric. If we talk about the metal film types, then these parts are really, so we use really here one metal film and then, for example, paper or plastic film, and you will wind that up, and this is then the total capacitor. The benefit of it is that you have really a high, these parts are really suited for higher currents, higher voltage applications. But the disadvantage is here for sure that you cannot get so much capacitance in the same package, like compared with the metallization on dielectric. And if we talk about metallization on dielectric, then you can apply the metallization on the plastic film. I show it here on the right hand side. So you can see here the black one is the dielectric material, and on top of it you have the metallization, which leads to the big benefit that you can that you have really thin layers, which allows you to reach high capacitance in the same volume. So this one is an example for plastic film, and you can also have it with paper film. Then I want to talk a little bit about some codes. For example, you can see the MKT, which is connected to polyester dielectric material, and then you have also MKP, which is used for the polypropylene materials. So let's talk a little bit more about the inner construction and also the safe healing process. Maybe to show you the inner construction of a X2 capacitor from our side. You can see here the winding, which is based on this inner structure. And then you can also see that there's a certain different distance between the first voltage level and the second voltage level to avoid short circuit or something like this. Then you have also the plastic box from the outside, and also the resin, which in the end protects the capacitor from moisture and also some other external influences. But what happens if there's some smaller failure inside of the capacitor? So you can see on the right-hand side, we have the metallization and the dielectric material. And for example, we have a breakdown due to surge. Then this could lead, if I have a very small surface, then you will have a very high current for a short period of time. And this very high current will lead to high temperatures. And these high temperatures lead to the fact that the metallization will be vaporized, and so you won't have any short circuit path here, which gives the advantage that this product is now repaired, and also the capacitance loss which you will have there is very small normally. So let's talk a little bit more about the safety part of the film capacitors. If we talk about X capacitors, then these X capacitors, they are placed between line and neutral normally, and they are especially designed for filtering of differential mode interferences. If we talk about Y capacitors, these are connected between line and earth and neutral and earth, and these are designed to filter common mode interferences. If we have a look at the safety class, for example, for X2, then this shows that the X2 capacitors, they have to withstand the 2.5 kV impulse voltage rating. And if we have a look at Y2 capacitors, for example, then you can see that they need to withstand so 5 kV impulse voltage tests. So this shows that for Y2 capacitors, the requirements are even higher because it's more important here. Because if you connect it to Earth, then it's here important to protect humans and animals from any bad influences there. So let's talk a little bit more about film capacitors and what we have to think about here. Especially if we talk about standard X2 capacitors, these types are cost effective, but for sure they have also resin and some other materials to protect it from humidity and temperature. But over long term and over some specific scenarios, they are sensitive to humidity and temperature. And we implemented some THP X2 capacitors, which use a very low moisture absorption and also some a little bit bigger sizes than regular X2 capacitors. And they show the benefit over long term that the influence of the humidity and the higher voltage is very low in comparison to standard X2 capacitors. And we also show this in a test. So the so-called 85-85 test over 300 volts AC after 1000 hours. And you can see that the regular capacitor, they have a fairly big capacitance drop after this test, and the typical or the THP X2 capacitors, they are allowed to have a maximum drop of 10%. I'm talking here about the type 3B types, but in a lot of cases, the degradation is even better for these THP types. So let's talk a little bit about DC-link film capacitors. They are used after the rectifier and before the inverter. They are used for higher voltage applications, like up to 1200 volts, which gives the benefit that you don't have to connect several of electrolytic capacitors in series and to balance them and so on. And there's also another benefit that they offer, a medium capacitance, medium-sized capacitance, which could lead that you only have to connect maybe not so many parts in parallel to realize your requirements of the applications. Let's talk a little bit about aluminum electrolytic capacitors. What I showed here is the inner structure of a hybrid polymer capacitor, but the inner structure of electrolytic capacitors, they look more or less the same if we talk about this picture here. So first of all, you can see the anode aluminum foil and then also the cathode aluminum foil, and in between there's a separator paper which is for aluminum electrolytic soaked with electrolyte. And then you have from the outside the aluminum can and then the rubber seal which protects the inner winding from drying out here. So let's talk a little bit more detailed about the different technologies which are in behind. If we talk about aluminum electrolytic, from the left-hand side, you can see the anode, and from the right-hand side, you have the cathode. And then you have in between the liquid electrolyte, so it's liquid, and you have also the oxide layer here. We can offer these parts with small packages, also medium-sized packages, and we have also big capacitors, big screw capacitors for these normal aluminum electrolytic capacitors. If we talk about aluminum polymer, then the biggest difference is that we have here a solid material, highly conductive solid material with no electrolyte. So in the end, it could not dry out like aluminum electrolytic ones. We only have the small sizes for these polymer capacitor types. And what we also have is small-sized SMD-H chip capacitors, but they are somehow limited in the voltage, so only available up to 6.3 volts. If we talk about hybrid polymer capacitors, then you can see that the hybrid polymer capacitor is more or less based on the aluminum polymer capacitor, but there's one additional production step. So afterwards, after you have the polymer capacitors, this winding will be also impregnated by some electrolyte, which gives the benefit that afterwards this electrolyte can give you also some self-healing behaviors, which could repair the oxide layer, which is shown here in black in your application. And we have also only the small sizes for hybrid polymer capacitors. So let's check them a little bit from the outside. For aluminum electrolytic capacitors, you can see them. They have a safety vent. We have the highest voltage ratings. Up to 650 volts is possible there. We have biggest sizes, and we have also some dielectric self-healing there. But the disadvantage is for sure that the electrolyte drain can somewhat shorten the lifetime. If we talk about aluminum polymer, you can see here that they don't have any vent with a very low ESR, which leads to high ripple currents and also a very, very long lifetime. But they are limited regarding the high voltage and sizes, which leads to the fact that regarding the manufacture, we cannot produce so big sizes for these parts. If we talk about hybrid polymer capacitors, you can see it for our parts. They don't have a sleeve. Sometimes for the bigger types, they have a vent, but because there's not so much electrolyte in it, we only need it for the bigger types. The advantages: low ESR, high ripple current, low leakage current. But the disadvantage is here also that we are limited in the size. So if we talk a little bit about the lifetime, then basically we have the classic Arrhenius formula, which is valid for aluminum electrolytic, aluminum hybrid polymer, and aluminum polymer capacitors H chip. And then we have also the other lifetime formula, which is factor 10 here, which is valid for aluminum polymer, THT, and B-chip SMT. You will also find the definitions, how the lifetime is defined in the datasheet, at least for the new data sheets. And we have also some end-of-life definitions here. Let's talk a little bit about the lifetime if you draw it over the ambient operating temperature. You can see here we did a comparison of aluminum electrolytic and aluminum polymer, and you can see that that aluminum polymer gets better if you reduce the temperature here. That's clear. And what we also show here is the hybrid polymer capacitor. And then you can see that especially for the higher temperature region, the hybrid polymer offers a higher lifetime for these parts. And then we have also our limit of 15 years for the recommendation. Yeah, and this one is more or less the same graphic, just a different style to show it. But yeah, same information more or less. So if we compare these different types with Red Expert, our online tool here, so I compared here 3 times 100 microfarad, 16 volts with the same package. Then you can see that, for example, if you check the ESR, then the polymer, they have the smallest ESR, which leads to high ripple current. If we talk about hybrid, then you can see that the ESR is also very small, comparable to polymer capacitor, but the ripple current is not so high like polymer capacitors for this specific part. If we talk about the leakage current, then there's a big benefit of electrolytic and hybrid ones. As I mentioned before, also hybrid ones have the ability to repair the oxide layer, which leads in the end to the fact that the leakage current can be also reduced over time. Yeah, if we talk about the endurance at 105 degrees Celsius, then you can see that the hybrid types, they offer very high endurance at high temperatures. If we do a calculation at, for example, normal operating conditions like 65 degrees, then you can see that with this specific case with hybrid polymer and polymer types, yeah, you get more or less the same limit here. And for the electrolytic one, the lifetime is very short in comparison to the other types. So yeah, let's talk a little bit more about the supercapacitors as the last technology. I just want to show why the capacitance is so high for these parts, and that's why on the right hand side I showed the inner structure, and you can see here also this type is also based on electrolyte. On the left hand side you have the electrode, which is based on on the right hand side you have the electrolyte, and then you have the positively charged cations, and on the left hand side you have like activated carbon. So carbon has a very high surface and or a very big surface, and also a high conductivity. And if you see here the positively charged cations, and in between of these cations and the negative electrode, there's only a very small distance, like the Helmholtz double layer, only several molecules. So you have a very small distance and high surface of this capacitor, which leads in the end to a high capacitance. Yeah, but also supercapacitors tend to reduce the lifetime based on the temperature from the outside and also the voltage. We have also some support notes about these topics, and we are also really supporting you here if you have some requests about these lifetime calculations for supercapacitors. And you can see it here. We showed here the relative C after 10 years. So for example, if you apply 2.3 volts at 40 degrees Celsius, you can see that the expected capacitance is around 60%. And for 2.7 volts and 40 degrees Celsius, the expected residual capacitance is around 20%. So sometimes it's important to do a lot of over design here. What I already mentioned before is that supercapacitors offer a very low voltage. And for example, if you're using 2 capacitors from different manufacturers and so on, which we really don't recommend, but it could happen that if you buy a capacitor with 10 farads and the tolerance is -10 + 30, for example, then you could get 2 completely different capacitor types, which in the end would lead to the fact that if you do the calculation here, that the parts with the lowest capacitance will see constantly over voltage if you apply the maximum voltage overall. So therefore we we really recommend to do some voltage balancing for these types here. And if you need some support here, or we're really willing to help you here to do the proper balancing in your design. So let's do a little bit of summary. At first, we talked about MLCC. They are very small. They offer high voltages. If we talk about class 1, low capacitance, but very stable. So low capacitance, very stable. Class 2, high capacitance, but not so stable. So very dependent on how high the voltage is and temperature. So they're very, very much a lot of dependencies. We have also safety capacitors for these types. So we have a lot of, a big portfolio for the MLCC. If we talk about film capacitors, they are very suitable for high voltages. They have self-healing properties. But it's important for these types to think about humidity and temperature when selecting these parts. If we talk about aluminum capacitors, or aluminum capacitors in general, then we can distinguish them between electrolytic and polymer and hybrid polymer. If we talk about electrolytic, they are the most cost efficient. We have big varieties in sizes. If we talk about polymer, then they are also they are suited for longevity applications. They show very low ESR values, which leads to the fact that you can apply high ripple currents. They are not suited for battery applications because the leakage current tend to be higher than electrolytic and aluminum hybrid polymer capacitors. And lastly, for this type, we have the aluminum hybrid polymer. They are also suited for longevity applications and also suited for high temperature applications, and gives the benefit that you can also apply high ripple currents on these hybrid polymer capacitors. So if we talk a little bit about the supercapacitors, they have a very high capacitance, but the issue is here we have only a small voltage. So if you need a higher voltage, you have to connect them in series, and therefore we really advise balancing if you use them in such scenarios. So thanks a lot. That was my presentation, and I'm really happy to answer your questions.
So Lukas, thank you very much for your presentation. It was very interesting. And as you can see, we did some arrangements here also in our studio in Munich. We hope you like it as well. So we like those arrangements. But now we have to keep on track. We still have some time for the questions. But first of all, I want to share the handout with you. So you now should be able to download the handout. And then we are heading right into the questions. So I see there are a lot of questions coming in. Probably we don't have the time to answer all of them, but then we will answer them later on via email. So then first question we see already, Lukas, the failure mode of Y capacitor cannot be in short circuit, but it can only fail in open circuit. Is that correct?
So what I have to say here is that the design is so that it's intended to fail open. That's clear, but we could never guarantee that there could be a short circuit, for example, if we talk about MLCC, then so there will be never a guarantee that they will not fail in a short circuit, but they are designed to fail open, so to say.
Okay, thank you very much. The next question, can I replace a film capacitor with electrolytic?
Yeah, that's a good question. It really depends on your application. So film capacitors and electrolytics, they have a lot of different properties. For example, electrolytic capacitors, they have a higher ESR, so you cannot apply so high currents there. But for example, if you are in the DC link area, then for sure for some applications you could replace it. In the end, it depends on the application really, but think about ESR and the impedance curve there.
Okay, thank you very much. Next question from Anton. What is the risk of repetitively using a film capacitor with higher than specified dV or dt?
Yeah, so the risk, the risk could, the question is how high is the dV/dt? Normally you will get, we'll see some safe feeding and the part won't be completely destroyed. But if you have very high dV/dt, then this could also lead to serious failures. Normally open mode. So it really depends on how high the dV/dt is.
Okay, thank you very much. If there are any questions open after our session, then you also can just email us and we will give you the answers. So then next question from Eldar. What is the maximum voltage of the supercapacitors available?
So from our side, it's currently 2.7 volts. In the market, you can also find some 3 volt, 3.3 volt types. But this is from my experience somehow the limitation. It's also possible that some manufacturers connect them internally in series and do some balancing to get a higher voltage from the outside. But yeah, these types are somewhat limited when it comes to the voltage.
Okay, so then last question, we have time for that. Does the Z formula here still apply to EDLC supercapacitors, the permittivity of which material is relevant here?
So I think this is a good question to go maybe a little bit more into detail. We have a good product manager for these parts, and I really would like to support here with the answering the question afterwards.
Okay, Lukas, thank you very much for all the answers, and so that was it from us today, and thank you also for your presentation, Lukas. It was a pleasure to have you here.
Thank you.
So then just stay tuned with our next sessions, and I hope you enjoyed it as well. And then I wish you a good day. Thank you for being here. Bye.
Bye.